Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find the minimum value of x? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Look at the blue right triangle ABC with its right angle at corner B. A point D sits on the horizontal side AB, and the slanted segment from C to D has length x. We want the smallest value x can ever take. Three facts are given. D is the midpoint of side AB, so segment AD equals segment BD. The area of the blue triangle ABC is exactly 1, and the segment CD is the length x we are tracking. Give the two equal halves of side AB a name. Call each of them A. Then segment BD equals A and segment AD equals A. So the full horizontal side AB measures 2A. Introducing A lets us track the figure with algebra. Now name the vertical side BC, the length B. With just the two letters A and B, every length in the whole picture can be written down, which is exactly what we need to compute x. Notice where the right angle lives. The two legs segment AB and segment BC meet at corner B, and that is the 90-degree corner of the blue triangle. Keeping this corner in mind is the key to the whole solution. Because D lies on the horizontal side AB, the segment DB runs straight along segment AB. So the smaller triangle DBC, shown in green, shares the very same corner B, which means angle DBC is also 90 degrees. In the green right triangle DBC, the side CD sits directly across from the right angle at B. So segment CD is the hypotenuse, the longest side. That hypotenuse is exactly our unknown x, which lets us bring in the Pythagorean theorem next. Apply the Pythagorean theorem to the green triangle. The hypotenuse squared equals the sum of the squares of the two legs, so x squared equals segment BD squared plus segment BC squared. Now put in our names. Since segment BD is A and segment BC is B, the relation becomes x squared equals A squared plus B squared. This is the quantity we want to make as small as possible. Right now, x depends on two free lengths, A and B. If both could shrink to nothing, x would too. So there must be a rule tying them together. That rule is the fixed area, which we bring in next. Bring back the big blue triangle, ABC. Because its right angle is at B, the two legs segment AB and segment BC serve as base and height, so its area is 1/2 times segment AB times segment BC. The problem tells us this area equals 1, so 1/2 times segment A, B times segment BC equals 1. This single equation is the link between A and B that we were looking for. Replace segment AB with 2A and segment BC with B. The area equation becomes 1/2 times 2A times B equals 1. Now everything is written in our two working letters. First insight is this. The area constraint collapses to AB equals 1. The geometry is now a clean algebra problem. Make A squared plus B squared as small as possible, while the product A times B stays fixed at 1. Let us solve that with one simple idea. A second insight now finishes the structure. A non-negative square gives the minimum. Multiply the square out. A minus B squared becomes A squared minus 2, AB plus B squared, and that whole expression is at least 0. Add 2AB to both sides. The inequality rearranges into a squared plus B squared is at least 2 times AB. Notice the left side is exactly x squared. Now use our constraint. Since AB equals 1, 2, AB is just 2. So a squared plus b squared is at least 2, no matter how the triangle is shaped. Because x squared equals a squared plus b squared, we now know x squared is at least 2. Taking the positive square root, x is at least the square root of 2, so x can never dip below that value. The smallest value happens exactly when our square is 0. That is when a minus b is 0. So the minimum is reached when a equals b, a perfectly balanced triangle. Combine a equals b with the constraint a times b equals 1. That gives a squared equals 1. So the only positive solution is a and b each equal to 1. So the answer is square root of 2. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.